Alright guys, hope you're having a good weekend because right now I'm actually doing some extra work uh, for recording some edit videos so that we can cover the missing materials from Friday's recitation 3 for the class 10601, Introduction to Machine Learning. Once again, I'm sorry for the timing problem that neither of the two sessions this morning actually got a chance to actually see all the problems that we prepared because we were simply just too ambitious trying to cover a lot of materials within a limited time frame. So this added video will be basically a sum up of what was going on this morning, and with more focused attention on other problems that some of you were actually missing during the morning's recitation. Okay, so we'll basically be focusing more on the kNN part, which is actually missed from the noon session, and also section 4, which was not covered during the 9 a.m. session. Okay, section 2 and 3 I think were pretty thoroughly discussed during the morning sessions. So if you have any more problems about these two sessions, by all means, come to our office hours, and we'll be more than happy to answer the questions regarding recitation as well as homework and anything else regarding machine learning, really. Okay, so let's dive right into it. For section 1, 1.1 and 1.2 is really just a refresher on how the general kNN algorithm works. So you start with a simple data set like this. Let me try to bring it up. Yep. Blue squares belong to one class, and red triangle belong to another class. Now you have a green dot, which is the unknown point, or the new point, or the or the tested point. Then the kNN algorithm basically follows that. First, we determine the value for k, which is termed a hyperparameter in this algorithm, because it's not determined by the model, but actually determined by the people who are using the model. Okay. So if we then after determining the value for k, we just find the nearest neighbor, k nearest neighbors from this green dot. And by nearest, we actually imply that we have to employ some kind of distance measure. Okay, and hopefully the Professor Kwon has already covered a lot of different metrics for distance that you can use. For example, the Euclidean distance, the L1 norm, and the Manhattan distance, taxi cab, a Frobenius norm, all that kind of stuff. Okay, so it has to be some kind of distance metric, and we use the metric to order the points, and then we just pick 3 closest. If k is 3, we just pick 3 closest data point, and then to classify the green dot, we just simply take the majority vote. All right, so in this case, the green dot will be classified by as the red triangle. Okay, so that's the kNN algorithm for classification. And section 1.3 is trying to cover another whole genre or category. Genre is such a fancy word. Another category, which is kNN for regression. So if you look at the data table, and excuse me for not blowing this window up because the data table window up, because I know everybody has the recitation notes, so this is really just here for reference. But the task here that we're trying to do is, given the quiz scores, actually scores for 2 quizzes of let's see, 7 students, and the grades, the final grades for those 7 students, how can we predict? Excuse me. How can we predict the final grade for, say, which I'm going to denote as F? How can we predict the final score for this the 8th new test point, the exact person? Okay? That's what the kNN regression is for. And in comparison to the kNN classification algorithm, kNN regression is really nothing much different. We still start with defining the hyperparameter for the k-value. Okay? We want the k-value, and in this simple example, we're going to choose k equals 2. And given this k-value, we need to determine a distance metric. And in subquestion 1.3.1, we're going to use the good old Euclidean distance. And if you work out the Euclidean distance, which is basically the squared sum. Hold on a second. So basically the squared sum between any rows here. I'm sorry, the squared sum of the difference between any of these two numbers here and these two numbers here, right? So just the good old definition of Euclidean sum, Euclidean distance. And if you work out all the details, which I will not cover just to waste your guys' time, then you can find that the two nearest neighbor for Zach will be, in this case, Kathy with a distance of 13, and David with a distance of 5. This is basically, let me just show you one detailed example, 3 squared plus 4 squared taking square root. Okay. All right, so that's it, finding the k-nearest neighbor. However, there is one added layer of complexity though, which is covered in question 1.2. If we were to choose a different distance metric, say Manhattan or the taxi cab distance metric, then even if we're fixing the value for k, we will still possibly arrive at different choices for nearest neighbors. And if you follow the definition of the Manhattan distance, the distance between Zach and David, as an example, will be basically David's 2 quiz scores, which is, let me see, 3 and 4, taking absolute value, add together, and that gives you 7. Okay? And you can see that if you work through all the other examples, then you will see that the next nearest neighbor for Zach will no longer be Kathy, but really Emily. And in this case, the distance for Emily is actually 16. And the distance for Kathy will actually change from 13 to 17. Okay? So the carry-away message here is to remember that the distance metric actually matters a lot in determining the k-nearest neighbor. Okay? So that's question 1.2. And now we have 2 nearest neighbor. Let's say it's Kathy and David. So we're using Euclidean distance. All right. Remember our goal. Okay. Our task is to predict the final score for Zach. Okay. And we do have final score for Kathy and David. One is let me try to look it up. One is 52. The other is 28. So the natural question is, how do we get from these two numbers to f of Zach? Right? And 1.3.3 raises one possibility. How about majority vote? For those of you with a keen eye, you should notice right away that majority rule would definitely not work. Why? Because we're no longer dealing with classification. We're dealing with regression problem. We're dealing with regression problem, meaning that our target variable, as given a particular sample point or a particular person in this case, this thing will actually be a continuous number. So that means that any value from 0 to 100 will actually have equal importance, right? Your final score can't be any number between these two numbers. And it really doesn't make any sense to actually say to take a vote between two numbers that have equal footing. Okay, so if you vote this over this, then are you saying that 52 is actually somehow more important than 28? Of course not. Both of them are possible final grades. Okay, so majority votes fails. Now 1.2.4 proposes another possibility. Well, how about we take average? So in this case, we're going to predict the score for Zach. Final grade will be 40. Okay, how does this sound? Well, it looks pretty reasonable. Well, in the sense that first, this thing is between 0 and 100. Second, since Kathy and David are the nearest neighbor for Zach, we kind of hope that the final grade for Zach is also a nearest neighbor of Kathy and David's final grades, which is kind of what the average is doing. It's trying to take the midpoint of these scores so that the final score is not too far from either of them, so they kind of stay close. Okay, so that's one possibility. And indeed, in real-world problems, a lot of people are actually simply using averages for kNN regression. Now, 1.3.5. However, there's something suspicious about 1.3.1. Sorry, about taking a simple average though. Because if we go back to, okay, I'm actually working with multiple windows right now, so it's a little bit hassle and bustle on my side. If we go back to the data table here, and you look at the quiz score, right? For Kathy and David, at least they got something during their quizzes. And for Zach, this is basically 0, right? So can we really say that Zach's score is going to be higher than David? Remember, we were taking just simple averages, so the average is going to be between these two values. Okay? Of course, now we were hoping to actually reflect in the final grade of Zach some kind of ordering between these sample points, right? Ordering between the scores of the quizzes between these three persons. Apparently, Kathy did a little bit better than David, who in turn does well, a little bit better than Zach. So we were hoping that Zach's score would be actually a little bit smaller. All right, and the way to do that is to see. And the way to do that is to actually, instead of taking a simple average, we can try to take a weighted average. By which we mean that the final score that you're trying to calculate would not be a simple arithmetic average of all the nearest neighbor that you find, but the nearest neighbor, the final score of the nearest neighbor modified or modulated or regulated, whatever you call it, by some kind of weight and normalized. This normalized factor here is just to ensure that the weight coming from these two coefficients will sum up to 1. Nothing special about that. Of course, we would prefer that all these weights are non-negative. Okay. So what could be a potential candidate for weight? Well, just by intuition, since we were using distance in our choice of nearest neighbor, in our search for Kathy and David, maybe we can use the inverse distance as our weighting parameter. You can see the meaning behind this right away. The closer the neighbor are, the closer the neighbor, the stronger or the larger the weight is, meaning that we think that they will have a much stronger influence on our final score. Right? So that's pretty intuitive. And if you work out the details, this kind of a recipe or our algorithm for choosing weight will give you for a Zach final score, let me try to look it up, something around 34.09. So it's not perfect. We're trying to find something that's smaller than 28, but at least we have bring it down from 40 to 34, so making it at least looks a little bit more reasonable. Of course, you can expand on this idea of adding weighted sum between the final scores, and expand on the choice for weights to many other possibilities, for endless possibility there. For example, there's one very classic weight measure. It's related to the Gaussian, so this is basically, let me try to make it correct, to gamma. Gamma, once again, is another hyperparameter you're going to choose, and multiplied by distance squared, right, e to the negative. This is inspired by the Gaussian distribution. So again, the interpretation is the same. The larger the distance, the larger this number is, the smaller this exponential will be. So it's like saying that the further your neighbor is, the less influence it will have on your data point. Okay, so it's pretty reasonable. And I won't go into the details of calculating the final score for Zach using this metric though. But just keep in mind that this is something that you can use in real data. All right, and let's see. This actually covers 1.3.5. And for 1.3.6, let's see. Okay, yeah, 1.3.6 is really a conceptual question. It's asking you, okay, let's take a retrospective look at all these predictions that we arrive at. We use the average to arrive at 40 for Zach's final grade, and we use weighted average to arrive at 34 for Zach's final grade. Do you think these are good estimates? Okay, this is really open-ended question. If we look back into the original data table, let me remind you that Zach did score 0 on both of the quizzes. So you would probably hope that a reasonable guess for the Zach's final grade would probably be less than like 20 or maybe 10. And apparently these two are overestimating that. They're just over-optimistic. But however, they do have solid logic background, right? Remember, we're taking simple average because we don't care about the order. We're taking the weighted average, and the weights actually have some kind of interpretation of, say, the influence of a particular neighbor depending on its distance. So both of these have some kind of nice interpretation, and they're very, very easy to explain to people who are trying to understand this problem. But you have to keep in mind that the result may not be optimal or may not be agreeing with your hypothesis, because remember, even if we say that we want, maybe in the ideal case that the score for Zach should be smaller than the score for David and smaller than the score for Kathy, there is no guarantee that this is correct. Okay? This is just another hypothesis, albeit kind of intuitive or correct, but hypothesis nonetheless that we have imposed on this problem. Okay, so keep this in mind. Once we impose some kind of hypothesis, it will actually help us to actually differentiate or differentiate the performance of different metrics or different algorithms that we choose to solve this problem. Okay, so that's how you do the kNN regression. So let's try to recap. Pretty much the same thing as the kNN classification. You select the number of neighbors, you select a distance metric, and then you try to figure out some kind of heuristic of dealing with the final target values. Either you take the average, you take the weighted average, and then there's actually one more fancy method. Say now you have Kathy's score, the final score, which is 50, I think, 52, sorry. And then you have David's final score, which is 28. And you have Kathy's quiz 1, quiz 2 value, David's quiz 1 and quiz 2 value, and then you have Zach's quiz 1 and quiz 2 value. We're trying to predict this thing. So let's try to focus on this subproblem here. This is picked out by our kNN algorithm. If you look at this, this is pretty much just like another regression problem, right? With a reduced sample size. So instead of having, say, 7 students, now you have only 2 students for 2 training samples, and you're still predicting 1 new data point. So there's another way that we can do, which is actually very popular in kNN regression, is after we pick out the nearest neighbor, the k nearest neighbor, we just do a linear regression. It is a regression problem, so we're going to do a linear regression, but on the subproblem or the sub-dataset that we picked out. Okay, and we use the whatever this linear regression model predicts as our final estimate for the final grade for Zach. Okay, this may sound actually most reasonable because we're actually not changing the nature of the problem. We are doing a regression, except that we're basically kind of doing a hierarchical regression in the sense that we're going to narrow down our focus on the values to regress by using kNN first, and then on the smaller subset, on the smaller data set, we're going to run a regular linear regression model. Okay, so that's it. This kind of idea of combining models at different levels. Say you start with an kNN model to deal with big data set, so as to filter out some smaller data set. Excuse my handwriting. and then you apply linear regression or any other model that seems to be more fitting to your task on this smaller data set. This kind of hierarchical structure is actually very common in real world when you're dealing with very complicated data sets, or when there's a natural ordering within the data set itself. Okay, so hopefully that covers the. Okay, there's one more question. Yeah, that covers the bulk of the meat in section 1. There are a couple more questions in section 1.4, but these are really not questions more than they are actually references. So you don't have to, actually there's no answer to any of the questions, I think. But there are a couple of keywords that we hope that you can actually go back and maybe have some time to actually look it up. For example, let me try to scroll it down there. For example, the curse of dimension, and also the Voronoi diagram, and also locally weighted regression. These are all key terms for you to search online and try to look into the details. Some of them are concerning the limitation of the kNN regression. Some of them are concerning the interpretation, geometric interpretation of kNN. And this is, once again, another fancy way of, after you finish with kNN, after you finish selecting the k-nearest neighbor, how do we do an even fancier version of this localized regression problem? Okay, so that covers section 1, and I will be talking about section 4 in the next video. Ciao.